Hey, welcome back. This is part 2 on the Deckel D-bit grinder wheel hubs, where we go from rusty steel to some nicely finished grinder wheel hubs. So let's get back into it. Only thing that's left is facing them to length and cutting the taper, and a little bit of drilling plus slotting, but that's minor. Let's do the math to set the compound slide to the correct angle to turn the ID taper. The Deckel D-bit grinder has a 5-in-1 taper. That means, let's draw a quick triangle here over a distance of 5 millimeter. We gain a diameter of 1 millimeter. And multiples of that, of course. So over 10 millimeters you gain 2 millimeters and so on and so on. But this is all we need to calculate the angle. We only want this. Half of the angle, half of the included angle is what we need. Let's call this alpha. So drawing a second triangle here. So that's the triangle up here is still 5 millimeters long, but only 0.5 millimeters, 0.5. And our angle is down here. So from our trusty book, it's this book, by the way, we know that tangent is A divided by B. So tangent alpha equals 0.5 divided by 5 is alpha equals tangent 0.5 divided by 5 is an angle of 5.7105 and some change. So that's 5.7106 rounded degrees. The angle doesn't really help us apart from looking at the graduation of the compound slide. What we want is a gauge block stack to set a sine bar. My sine bar has a roller distance of 50 millimeters. So what we really need is x, that's our gauge block stack, equals the sine of this angle, but we're not going to use this rounded number, we want the exact number, sinus. And then we just take this and put it in here. Minus tangent. How do you write this? That's tangent 0.5 divided by 5, closed brackets, and times the roller distance. So x equals, let's clear this, sinus tangent of 0.5 divided by 5 bracket times 50, enter, and then this is our gauge block stack, 4.975. 4.975. Going to use the tiny sine bars that I made ages ago. Here's a video on these. 2016. There are my gauge blocks that I need. For gauge blocks, you can either run them very carefully over a set of precision ground flat stones, or, what's also quite nice, it's just a piece of paper to clean them before ringing them together. No, this won't alter their dimension. Don't worry, it's fine. So, building the gauge block stack, just pushing them together, ringing them together, as we say in the industry, And I always like to double check my gauge block stack up. Yeah, it should be 4.975, but I will give it those, I will give it that. That's me handling these with bare hands, thermal drift, tolerances in the gauge blocks. It's all adding up. But I'm not, there's a little bit of a thunderstorm outside, but I'm not building a rocket ship here, so I will be fine. Making sure the backside of the compound is clean and burr-free. The precision magnets are kind of a nightmare to keep clean, by the way, because they are magnets. That's why I have to laugh always when somebody recommends, oh, just put magnets in it. Magnets are a nightmare in a precision environment. It's really, really hard to keep them clean enough for this level of precision. If you don't have or don't want to use magnets in this application, you can also just take a nice 123 block and clamp it against the side of the compound slide with a large clamp, and use that as a reference edge. You need to make sure that the side of the compound slide is, of course, parallel to its travel. That you do that by just resting a indicator against it and moving the compound back and forth. If that stays 0, you're good to go. Let's find a wrench. Let's open these two nuts. We want to go this direction, so the sign bar has to be like this. We slide our gauge block stack in place on the magnet. And we bring the sign bar in place, and we add a rubber band around everything, like this, so the sign bar is in place when we move things around. Now it's just a matter of, that's way too much. Now it's just a matter of moving the carriage back and forth and adjusting the angle of the compound until the needle shows 0. This is dropping, so we need to go this direction. You can speed this up dramatically by just moving very slowly, looking at the needle and adjusting while you're moving very slowly. Okay, that's pretty darn good. Keep in mind we're measuring over a distance of maybe 40 millimeters, and the taper of the D-bit grinder is only like 12 millimeters long. And now we tighten the nuts of the angle adjustment, and then we start over because it moved a tiny bit when I tighten it down. That's how it normally goes. I usually tighten it a little bit, adjust if needed, and then I tighten it down to full torque. On such a small machine like this, you really don't need to gronk down on this. You look where I'm grabbing the wrench with like 2 fingers. That's all the torque I put in there. And no need to grab the outer end of the wrench and give it a full upper body pull. We are precision machinists here. There is a little bit of a common sense when it comes to torquing things. There is a time and place for a breaker bar, but adjustments and setting machine tools is not one of them. So that's the angle setting. That's really important to get this right, and you do this properly. I only can recommend doing this with a sign bar. I'm going to show you the other method too that I do not like, but for sake of completeness, I will show it. So you have an indicator, it's set on center height as good as possible. and it's square between something in the chuck and the indicator stem here. And this works best if you have a DRO, but it works without one too. The next thing is you zero it out in a convenient spot. Then you move the compound by, for example, since it's a 5-in-1 taper, you move it by 5 millimeters. Then we should have 0.5 millimeters of change here on the indicator. This is not really correct because by moving at an angle, we're measuring hypotenuse, the hypotenuse, the longest side of the triangle. But for small angles, this can be neglected. So we move it by 5 millimeters, 3, 4. I'm looking at the DRO. So this is exactly 5 millimeters, and we have exactly 0.5 millimeters of change here on the dial test indicator. So we just double checked our setting with the sine bar, and this is an alternative method to the sine bar. I prefer the sine bar, some people prefer this. I'm not the biggest fan of it, but it works. I'm going to use the 6th jaw. This works quite well for this application. I could change over to either collets. I could hold the wheel hubs in a 20 millimeter collet on this diameter here. This is perfectly fine. Or I could bore soft jaws, or I can just go with the 6th jaw, which is adjustable for runout, and use that. So part goes in here. This is the most simple way of holding this. Just chuck it up and take an indicator. And we check the runout. Shouldn't be too terrible. It's like 40 micron here. Let's adjust this to as good as possible, because this determines the runout of the final wheel hub. This outer diameter was cut in the same setup as the 20 millimeter centering diameter for the grinding wheel, so I can use this as a reference for setting the trueness, how true it runs. Wow, my English is falling apart. Well, let's adjust this. Just a wee bit. Another tiny bit here. I could use the electronic indicator too, but this Giraud, this has proven to read extremely sensitive on small adjustments, so it's perfectly fine for this level of precision. When I adjust the set true chuck, I adjust like this, and then I back the set screw off a little bit, so if I'm adjusting on the other side, I'm not fighting the set screws. Yeah, that's one needle width. That's perfectly fine. That's probably better than using collets. I really like an adjustable chuck. Nobody should buy a new chuck that's not adjustable for runout, or not create any provision to adjust the runout, like machining the register diameter on the back undersides and just using a copper drift and the screws loosened a little bit to knock it true. Every chuck should have some way to set it true. Otherwise, in my opinion, it's just a roughing tool. Roughing or first operation work holding. There might be a point to, well, yeah, a 3-jaw chuck is a first operation work holding, but it can be so much more, as you see. I can just come here, grab a finished part, adjust it for runout, go from there and move very, very fast without having to muck around with soft jaws. If I cannot bore soft jaws, I'm a very happy person. It's quite the annoying work for me. One additional thing that I made off camera is a test bar. I took a piece of 16mm case hardened rod, chucked it up in the spin fixture in the grind awl, and I ground the 1 in 5 taper of the D-bit grinder onto the end of this piece of hardened stock. Clever as I am, this has 16mm OD, and the 16mm is the gauge diameter of the taper in the wheel hubs. And I added a little bit of a groove exactly where the 16mm diameter transitions into the taper, and this tells me how far I have to move in. And also it's to check the taper fit, of course. That's, by the way, a very loud boring bar. It's solid carbide, but it gets into a weird harmonic that well, it's there, but it doesn't telegraph into the surface finish. Not very much, at least. And by the way, yes, you can use a power drill or cordless drill to run the compound slide. I have done that in the past too, but to be honest, good technique by hand feeding is most of the time fine. What do I mean with good technique? Well, feeding hand over hand. You start like this with your dominant hand. You turn until you almost wind yourself up, and then the other hand just continues the motion. That way you can get a very, very fine and very controllable feed without putting, like if you crank like this, you get this wobbling motion that will translate through the to the play in the dovetail of the compound slide. You will get a wavy surface. Even with a very, very long dovetail engagement like on the Weiler compound slide, it's still not perfect. So this technique here doesn't put any sideways motion on the compound. This is this is how we learned to do it in apprenticeship, not like this. You can do this for rapid motion, but for precision movement, like this. It's way, way better, and also you can stop pinpoint accurate compared to this. This is way more stable, or this. They gave you this entire hand crank, so use it, not just the tiny handle here. Sometimes you can also grab the knurled ring back here. That's also on some machines quite nice. Depending on, that's a little bit personal, depending on how you like to move your hands. To give you an idea about the test bar, about the groove for the gauge diameter, here you can see the groove, and this edge here of the groove needs to be flush with the back face of the wheel hub. Then the taper diameter is big enough. And also it should not drop in any further, of course. It should be very much flush. There is, of course, a tolerance, a pretty wide tolerance, but I like to have all the tapers sit kind of in the same spot on my machines. Okay, that was the final cut. Now we retract the tool inwards and move it out like this. There we go. That's one wheel hub taper turned. Should probably check it before doing anything else. Let's get back to a higher RPM. Also, the leading edge here needs to be deeper than chamfered. And I will also run a piece of Cratex through the bore to remove all of the surface noise from boring. So first, double checking with my taper gauge. Yeah, that's good. That's good. I have a piece of Cratex super glued to a piece of square aluminum, and I will just work it through the taper bore to clean any remaining surface roughness from the boring. Despite having way covers, I will put something here. That's too slow. You can really polish with the Cratex in a precision bore without altering its diameter or geometry much. You will probably die of old age before you alter the geometry. Using a round stone to round over the edge. Chamfer. After doing the Cratex, it should be 100% safe to touch. Rounding the inner edge of the chamfer that meets the taper is important, because otherwise it's still a sharp edge. It can't scrape off material off your very valuable spindle taper. Yeah, very happy with the result. No damage from the 6-jaw chuck, perfectly fine. We need a slotting tool to cut the 3.2mm keyway, and for that I found a piece of 8mm round high-speed steel. Changing to an aluminum oxide wheel for grinding high-speed steel. The full width plunging with the wheel dulls the wheel very quickly. So now we have this hook shape, and we will only grind a little bit of relief on this remaining material in front here, like a few degrees. But let's clean the grinder first before we do any adjustments. To grind the side clearance or front clearance, what do I know? We just tilt it like this by maybe 5 degrees should be plenty, and we just clean up like this. Okay. For the actual cutting rake, I guess, we go to 90. Well, we go like this, and we tilt in 5 degrees, like this. And then we just clean up the cutting edge like this. I'll just feed in and clean up like this, and this is the final cutting edge then. slotting head is mounted to the mill, and here's my adapter to run small 8mm shanked slotting tools and the slotting head. This is a 16mm square shank. It just has an 8mm hole, and it has a register flat, so you put this in the tool holder of the slotting head and you move it all the way up against the face of the ram, and it self-aligns with the bolt, and then you just tighten it down. And the actual slotting tool goes in this small adapter. I'm going to slot to the side, because since we have a tapered bore, we have to tilt the slotting head a little bit. Aligning the slotting tool with the x-axis travel of the mill just by traversing back and forth, and I'm going to rotate the tool until the dial test indicator doesn't give me a reading anymore. So to grab it, I like to use a small toolmaker's clamp, or you can also use something like parallel pliers. So I think we need to go this way. This is really not hard. There we go, that's aligned within 20 microns already. A little bit like this. Hello? Let's go this way and finally clamp it down. It's not like this thing is going to fly to the moon. So 0 on this end of the tool and 0 on this end of the tool. For centering the indexing head to the slotting tool, or for centering the slotting tool to the indexing head, I like to use this method the most. I have the dial test indicator on a Mac base spinning with the indexing head on an arbitrary radius. I'm just moving up the tool towards the dial test indicator. I find the high point and I zero out the DRO in this position. And I retract the slotting tool, crank this by 180 degrees, do the same on the back side. And I split the y-axis value into half. I crank to 0. And then I am perfectly on center line with the rotation of axis of the indexing head. No guesswork there. This is as good as it gets with the setup. I put the dial test indicator in the tapered bore, and I found the low spot in the y direction. Otherwise, your angle that you're tracing with dial test indicator against the bore will not be true. Same problem as if you bore the taper with a tool that's not on center height. And I already knocked the head in position, so the angle of the head matches the angle of the taper. As you can see, when I move up and down, there is very minor deviation on the dial test indicator. The machine RPM is 100 RPM, and this gives on the slotting head 40 double strokes per minute, so up and down. That's one double stroke. Already checked my clearance. This is very important with a slotting head or with any shaper in general. You don't want a collision with one of those. I'm advancing about 50 micron per pass. go. Quick look at the slotting tool here. I think you didn't see it very well in the grinder. This here, this is the cutting edge. And everything else is just clearance. I think you can see that only the cutting edge in front here is making contact with the calipers. Everything else clears the calipers, and that's the important part on any cutting tool. You need a cutting edge and you need clearance on everything else or it will rub. The actual angles on such a tool are not critical. Let's call it that. I wouldn't say they don't matter, but they are not as critical as some people think. If you do like 5 degrees for the major clearances like here and here, and 1 or 2 degrees on everything else, perfectly fine. It just can't rub. This is not a high production tool that is made for massive material removal. This is a tool room job here. Don't overthink cutting tools. And here are the chips. Produced by this tool. Nice little curls. I have one of the finished wheel hubs mounted on the D-bit grinder. I only put it on the taper and gave it a little bit of a tap with a copper drift, because without a grinding wheel on it, I don't have anything to hold it to tighten the nut. And I have a 1 micron reading Mitutoyo Hikator, which is a rebranded Mar Millimesh, held in a collet in a little right angle holder that I had, and I can check the runout with it. I can move it to 0. Keep in mind that this machine is not the stiffest affair in the world, so let's spin the spindle slowly from hand. Keep in mind each division on this indicator is 1 micron, so that's really not very much. Oh wait, I can spin it by touching the pulley here. That's better than trying to touch the wheel hub. So yeah, that's pretty much the lowest point, -1, and it's moving up to barely 5 micron. So -1 to 5, 6 micron total indicator runout on the wheel hub. That's not taking runout of the spindle taper of the D-bit grinder into account. So quick look at the tools that I used. The roughing tool that I used is not really a roughing tool. It's a CCM-T06 insert, which is a dinky little carbide insert with 6mm length on the sides, and this is even a 0.2mm corner radius, so not really a roughing insert, but in my context it works quite well. This is sold as a finishing insert for stainless steel, but it turns out that it's a great universal insert for what I do. These are relatively inexpensive. They are like $7 a piece, have 2 cutting edges, and cut very freely. Work quite nicely. Not ideal. My finishing insert is a DCMT insert. This is a geometry for steel and stainless, but has its periphery ground, so it's sharp. There's a relatively sharp edge. Let's see if I can get this. This surface here And all the clearance surface all around the insert has been ground to create a cutting edge with a minimal corner radius, or edge radius, sorry. And this creates an insert that is very, very free cutting, leaves a good finish and works in problematic situations, in problematic materials. Not cheap. These are, I keep these to finishing and specialty materials or special projects where the price of the insert doesn't matter too much. Quick mention of the chamfer tool, just a piece of 10mm carbide round stock that's split in half on the surface grinder. Has a 90-degree tip ground on it and some clearance angles. Both sides ground, so I can use it ID and OD in different orientations. The boring bar, this is a shop-made carbide boring bar. This is 6mm carbide round stock. And I cut off pieces, I think it was 10mm in diameter carbide, and I braced it on, oops, to give me the offset to clear the shank of this boring tool with the cutting edge. So brace it on, and then I ground everything on this tool. I have a picture here where you can see the braced on head and a few steps on the surface grinder to create the overall geometry. I think you could do this on the D-bit grinder too, but I didn't have one at the time. So this is a very, very economical tool, very cheap to make. It's just carbide. I think I made 3 in total. And here you can see, I left the shank fairly long to give me all the reach that I need. And if the head is worn down enough and can't be resharpened anymore, I can just unbrace it and brace on a new head if I want to. The boring tools, that's where I like to make my own stuff. But with threading tools, well, if possible, I like to buy something. ER16 OD threading insert. As I mentioned, these are full profile inserts. They cut the profile and top the OD of the thread with this geometry here. So you create the true shape of the thread as it's stated in the standard. And same for the ID boring bar. This is not the insert that I used. This is a partial profile insert. This can cut a wide range of thread pitches, but as you can see, it's super pointy here and will not create 100% correct thread form. Here is a 1mm pitch insert. As you can see, it's far less pointy out here. This comes to an actual point, and this has a small radius ground onto its tip, and also it can't cut as deep because this also cuts the crest of the thread once you go deep enough. So these, if possible, I use these. These are they're my wild card for threads that I don't have a topping or full profile insert for. I like to have both at hand, but this is my preference. Machining the nuts for the wheel hubs, I'm using a slug of the same 42 chromoly S4 steel, and I'm drilling out the center using a core drill or a rotor broach. These drills are very economical on their power usage. You can push them quite hard on a light machine like this. I prefer them whenever possible over a twist drill. As you can see, they leave this slug of material. Turning down the OD, this time I'm using a CNMG insert. This really breaks the chip very nicely. Using a high-speed steel parting tool to part off the individual nuts. Running flood oil here. The high-speed steel parting blade is not ideal for this task. You have to go relatively slow on the surface speed, otherwise you burn up the edge, but it worked. Holding the blanks for the nuts in soft jaws this time, so facing them to thickness, chamfering, flipping them around and adding the same relief cut that I did on the wheel hubs. In the same setup, boring the ID for the M20 by 1 fine thread, adding the chamfer, setting up the boring bar, the threading boring bar. Last time I used it, I had a partial profile insert in it, but now I'm changing back to a 1mm pitch full profile insert, which makes threading so much easier and so much nicer. When you change inserts on any tool, make sure the insert seat is clean. Don't clamp the insert onto chips. It can crack the insert and also can damage the boring bar itself. Engaging the half nut of the Weiler lathe and threading away on the nut. I usually leave the half nuts engaged while I thread, and I do a straight infeed. I do not turn the compound to 60 degrees or 30 degrees depending on how you measure. I don't think it's necessary for small pitch threads up to maybe 2-3 millimeters of pitch. As you can see, I'm just straight out feeding. My right hand is turning off the spindle and reversing it. It's just out of frame. My left hand is doing the cross slide controls. This is where a spindle brake is really nice to work with. Cleaning it and test fitting. And it appears I'm happy with the fit. Redoing the chamfer. Threading always throws a little bit of a burr, so after threading I usually come back with the chamfer tool and remove that burr. Cleaning the soft jaws, flipping the nut around and chamfering the other side of the thread. My soft jaws look a little bit funny, but I found that it's very easy just to buy a round bar, saw off pieces of it and mill the contour for the carrier jaws into their backside. Here I'm drilling the pin spanner holes into the nuts. Super simple setup on the Deckel, just using the indexing head. As you can see, I'm sitting here running the milling machine, and being tall really lends to operate this machine for certain tasks while sitting. It's very comfortable, especially when you do repeat parts where you do, for example, just drilling or just milling one step at a time. So the original wheel hubs had a slot, or a key slot, and a washer with a small nose to prevent them from rotating. Normally you need this only with spindles that can be ran in reverse, so the wheel washer and nut combination doesn't unscrew itself from the wheel hub, which is a very exciting moment when that happens. The SO grinder cannot be ran in reverse from factory, so I'm not 100% sure why they included it. Probably because they thought it would be nicer if the washer stays stationary while the nut is tightened, so you don't crush the grinding wheel with a spinning nut washer combination. So that's why I think they added it. Deburring the wheel hubs using a round stone to break the edges of the internal keyway. You hear the CNC in the background going along. Using a die grinder with a rubber bonded abrasive wheel to deburr the key slot in the thread, break all the edges, round everything over, make sure there are no burrs, just make a clean product. I'm doing a cold bluing or cold black finish. For that, I first clean the parts with isopropane alcohol, blow them dry. Before applying the cold blue, I used a activator which kind of etches the surface a little bit and makes it more reactive to the cold bluing solution. You're supposed to apply to the surface and wait maybe a minute or two. In this case, the activator already reacts with the alloy elements of the 42 chromoly and leaves a grayish surface that can be rubbed off. I washed the activator off with some isopropane alcohol after my waiting period, and then I apply the cold bluing solution. I never take the cold blue with a brush directly from the container. I found that this is a very, very easy way to contaminate the cold bluing solution in the bottle and ruin it. Always put it in a separate container, use a new brush, and never put the used solution back in the bottle. It will ruin it. Then it's just a matter of applying the cold bluing solution to all the surfaces and give it a few minutes. I also noticed that doing the cold bluing in a two-step process is also beneficial. So after the first time using or applying the cold bluing, I'm using 4O steel wool, and I polish the entire part quickly down. This removes quite a bit of the cold bluing again, and afterwards I go back into the cold bluing solution and reapply it, and this gives me usually a way nicer finish, or a way more even finish. So here I'm reapplying the cold bluing after polishing it with the steel wool. So after washing the parts, I will add a generous amount of a thin rust protective oil, and I will have the parts sit overnight covered in oil. Some of the oil will move into the oxide finish and stay there. And this is also what makes the finish kind of durable. Here are the 6 wheel hubs and nuts finished after cold bluing or cold blackening, and the results are really nice. I'm not going to remachine or clean up the precision surfaces. The cold oxide finish adds so little of surface thickness, it's not a problem. But overall, I'm very happy how they came out. This is the original one that I purchased from Franz Singer, and that's one that I made. As you can see, the purchased ones, the nut seems to be Blanchard ground on one side. I'm very happy. This, well, I'm happy. Quick look, this is my current selection of wheels I have for the D-bit grinder. This is an 80 grit aluminum oxide wheel for steel, for high-speed steels. This is the very classic wheel that you usually get. The outer layer is reinforced with a resin, so it keeps its corner better. And you really wear down this corner because it's doing all the work, for example, when you split a high-speed steel blank in half. Not very expensive. This is my current main diamond wheel. It's a cup wheel. Well, it's a saucer wheel, I think it's called. A very sharp corner, good for detail work. And the diamond is very narrow. And I purchased this under the idea that the smaller contact patch is less strenuous on the motor than with a wide diamond band like on this wheel. And so far, this theory has proven well. Of course, since there is less diamond, it wears down a little bit faster, but there is always a little bit of a compromise. Grit on this one is D125. This is a very generic roughing grit. Then I have this one. This is I think it's D40. D40, a very, very smooth or very, very fine grit diamond wheel. This leaves a near mirror surface finish without lapping. Well, my old day job, we used to call them lapping wheels, but they're not. They're resin bond diamond wheels. And on one of my shop-made arbors, I made a little bit of an aluminum spacer because this wheel body is very thin and the thread on the hub doesn't go back far enough to clamp it. So there is the aluminum spacer. And this is just a straight 1A1 wheel that can be used on both sides. Certain tools like when you grind a thread mill on the D-bit grinder, you need to grind on the back side of the wheel. Sometimes you can flip a cup wheel on the hub, or you use a 1A1 wheel and grind on the other side. So that's my current setup. I want to get a resin bond cutoff wheel diamond for carbide, but for that purpose I would prefer the extended wheel arbors that are still in the rough here. So yeah, now I still have 5 wheel hubs spare, which is very nice. It saves you from flipping wheels around on the arbors. So that's it. That's 6 of these wheel hubs all finished and ready to go. This this video has dragged out quite a bit, but I wanted to go into painful detail. I hope you enjoyed. I hope you learned something. Thank you all for watching. Thanks for your support, and I'll be back.